Hello, greetings from Rutgers. We would like to present to you graph cities. Our aim is to provide a means of visually exploring large graphs. So what does it mean for a graph to be large? For computers, we consider a graph to be large when it doesn't fit in random access memory. But for humans, we are limited by how much we can perceive. Some constraints include the size of our screens and the computational ability to render graph layouts dynamically. Thus, a desirable graph exploration system should be computationally efficient for large graphs while providing interactive control without overwhelming the user. Previous work proposes a decomposition algorithm that partitions a graph into sets of edges called fixed points of degree peeling. As the name suggests, however, the same decomposition cannot be used to further decompose fixed points. To deal with large fixed points of degree peeling, we leverage a recently proposed work to decompose them into graph waves and fragments. Similarly to how fixed points form an edge partition of a graph, waves form an edge partition of a fixed point. Waves are constructed from a sequence of fragments in the following way. Given a fixed point with minimum degree k, we take the vertices of degree k as an initial seed set. The edges with at least one vertex in the seed set are labeled as the first fragment and removed. Once removed, the degree of the fragment vertices that were not in the seed set are updated and those with degree less than k are selected as the next seed set. Again, we label the edges going out of the seed set as the next fragment, remove them, and update the degrees of the affected vertices. We repeat the process until there are no remaining vertices, or the remaining vertices have degree greater than or equal to k. All the edges removed so far are labeled as the first wave. We start again with a seed set of degree equal to k, and repeat the process until the fixed point is empty. In the example on the left, the blue and green edge fragments make up the first wave of a fixed point of minimum degree 2, and the red edge fragment makes up the second wave. The picture on the right shows a collection of 19 fragments colored blue to red from a wave in the Friendster social network. We represent fixed points as collections of waves through the metaphor of a building with floors. Each wave maps to a floor with its volume and disk areas corresponding to its size and edges and vertices, respectively. The color hue indicates density. Connected fixed points of degree peeling are grouped together into buckets according to the number of edges. We render a building for the largest fixed point in each bucket. A few fixed points in the bucket are uniformly sampled to be drawn as bushes on patches of grass. The dimension of the grass patch indicates the total size and number of other fixed points. Bushes are a rougher representation of fixed points than buildings. To generate a bush, first the skeleton is created based on the same parameters of a given fixed point as those used for the building representation. Then a few iterations of an else system are executed with initial points distributed along the skeleton in order to render the final bush image. The flags on top of buildings display various summary information. For buildings that are alone in their bucket, the flag shows the number of floors, the peel value, and the size of the corresponding fixed point. For buildings part of a larger bucket, the flags show a plot of the distribution of peel values of the fixed points in that bucket. The graph city is the total collection of building, buckets, and bushes. The city is drawn in a spiral layout with larger fixed points in the center. Additionally, we draw a street network between buildings to indicate the amount of shared vertices between the corresponding fixed points. Here we show an up-close view of the graph city of the Friendster social network, which has over 65 million vertices and 1.8 billion edges. Notice that the outside of the spiral has many buckets of small fixed points, whereas the inside of the spiral has a handful of large fixed points which stand on their own. This is indicative of the fact that the dataset follows a power law, which makes intuitive sense for a social network. The city can also be viewed in night mode, which adds a checkerboard pattern of lights to all the building floors. The light intensity at each floor is proportional to the number of vertices shared between the set of edges represented by that floor and the complement with respect to the whole graph. Selecting a building allows the user to explore the local fragment structure of the graph for that fixed point of degree peeling. The fixed point is drawn in 3D as a metagraph of the connected seed sets. Selecting one of the metanode seed sets will bring up a view of the corresponding subgraph. In addition to the city, we produce a summary sculpture for an entire dataset. This sculpture gives a preview of the distribution of fixed point peel values and sizes. The aspect ratio of the sculpture encodes the average gap between consecutive peel values. The taller the sculpture, the larger the average gap. Although large fragments are rare, we still want to offer the user a way of exploring their structure. To draw large fragments, we propose a two-step iterative process. First, we delete all edges with peel 1 vertices as endpoints. Then we perform a maximal matching edge contraction. We repeat these two steps until the remaining graph is small enough to be drawn. In summary, we take as input a large graph. We use the iterative edge chord decomposition to decompose the graph into fixed points, and then further decompose the large fixed points using the wave decomposition. We group together similarly sized fixed points and map the output of these decompositions into a city metaphor of buildings and bushes. The city is rendered as part of an interactive interface which allows the user to select buildings and explore their local substructure. We are currently working on extending our approach to allow for streaming and more functional end-user features. For future work, we are interested in exploring how to use subgraph patterns found with our interface for semantic data summarization, and explore which graph problems can be more easily solved by composing solutions of fixed points, waves, and fragments. Thank you for watching and listening to this presentation, and special thanks to the NSF for supporting this project.